One of the most prominent and distinguished physicists of our time, Michio Kaku, has recently shared his perspective on a groundbreaking issue in the field of astrophysics. Kaku, renowned for his remarkable contributions to the study of physics, confirmed that the James Webb Space Telescope, JWST, has discovered 6 massive galaxies that scientists previously believed could not exist. These findings have the potential to revolutionize our understanding of the universe, offering exciting new possibilities for scientific exploration. Kaku's acknowledgement of this discovery is both fascinating and significant, especially considering his stature as a leading physicist. An expert in both classical experimental physics and quantum mechanics, Kaku has long been open to new ideas, unlike some more conservative colleagues in his field. As a physicist of both American and Japanese heritage, Kaku has consistently demonstrated a willingness to challenge established norms. While many researchers remain skeptical about the implications of the JWST findings, Kaku has embraced the potential of these discoveries. He is visibly enthusiastic about the revelations made by the telescope, openly sharing his excitement about the 6 massive galaxies that have now been identified. His comments underline the significance of these findings, which he believes will prompt a major shift in our cosmic understanding. Throughout his career, Kaku has been receptive to new hypotheses, understanding that scientific progress often comes through rethinking long-held assumptions. He is well aware that theories such as Einstein's relativity and Newton's laws of motion do not account for all the complexities of the universe. The discoveries made by the JWST, according to Kaku, have the potential to significantly enhance our knowledge of the cosmos. Even though many of his peers have been slow to accept these new ideas, the revelation of these galaxies, which appear to predate the conventional formation of galaxies, challenges the very foundations of modern cosmology, triggering intense debate among scientists, both proponents and critics of quantum mechanics. Yet Kaku, ever the optimist, dismisses the concerns with humor, suggesting that such skepticism is nothing new in the history of science. The galaxies discovered by the JWST date back to the early epochs of the universe, existing only 200 to 700 million years after the Big Bang. These extraordinary galaxies contain more stars than our Milky Way despite their early formation. They have been dubbed universe breakers by the astronomers who made the discovery, as their existence could fundamentally alter our current understanding of galaxy formation. According to the prevailing Big Bang theory, the universe was initially a hot, chaotic state, and it took many millennia for the first solid structures to form. Complex structures like galaxies were believed to emerge much later in the universe's history. However, these new galaxies contradict this timeline, as their enormous size and luminosity suggest that they were actively forming stars at a rate much higher than that of the Milky Way, which forms stars only intermittently. This discovery raises critical questions. Is the universe much older than previously thought, or did complex structures like galaxies form much sooner than our models suggest? This is a particularly challenging dilemma for conservative scientists, many of whom still cling to outdated models. Some researchers have already raised concerns about the accuracy of the age calculations, but Kaku, drawing from the history of scientific discovery, insists that such theories are often stubbornly upheld even when they are later disproven. History has shown that new research can expose flaws in long-standing theories, and Kaku asserts that the key to scientific progress lies in experimentation and open-mindedness. The Big Bang theory, first proposed in 1927, has long been the dominant explanation for the origins of the universe. Based on observations of the universe's expansion, the theory suggests that the universe began from a single point and has been expanding ever since. At the time, the idea of a universe with a definitive beginning and an inevitable end was difficult for both scientists and the general public to accept. Even today, the idea of an expanding universe is hard to grasp fully, and the theory continues to face scrutiny. Kaku emphasizes that science must remain flexible, acknowledging that what we once believed to be absolute truths may, in fact, need re-examination as new data becomes available. This openness to new ideas is especially crucial as we consider the implications of the JWST findings. The discovery of these 6 massive galaxies, seemingly formed much earlier than expected, compels scientists to reassess long-standing assumptions. Science, Kaku reminds us, has always advanced through the willingness to question existing models. Just as early astronomers believed in a geocentric universe before evidence proved otherwise, we must now entertain the possibility that our current understanding of cosmic history may be flawed. One of the key tools that scientists use to measure the distance and speed of celestial objects is redshift, a phenomenon where the wavelength of light from a moving object shifts towards the red end of the spectrum as it moves away from the observer. Redshift is commonly used in cosmology to calculate the expansion of the universe and the movement of galaxies. However, as Kaku points out, even small errors in these measurements could lead to significant misinterpretations. The methods previously used to calculate redshift are currently under review, and new techniques may yield different results. The recent discoveries made by the JWST bring this question to the forefront. Are these new findings based on redshift errors, or do they reflect a genuine challenge to the current understanding of the universe? The James Webb Space Telescope, with its advanced technology, is capable of observing the most distant reaches of space with exceptional clarity, revealing light from galaxies formed billions of years ago. Its discovery of ancient massive galaxies has defied predictions made by existing models of galaxy formation, which suggested that such large structures should have appeared much later in the universe's history. This discovery challenges not only our understanding of cosmology, but also the fundamental physics that underpins it, urging researchers to reconsider the Big Bang Theory and other long-established concepts in light of this new evidence. In conclusion, the discoveries made by the JWST underscore the dynamic and ever-evolving nature of science. As new evidence continues to surface, it becomes increasingly clear that our models of the universe must remain flexible, open to revision, and receptive to new ideas. The findings of the JWST, particularly the discovery of these 6 massive galaxies, represent a significant shift in our understanding of cosmic history. These revelations may not only change the course of astronomy, but also reshape the fundamental principles of physics, prompting further exploration and refinement of the theories that explain the universe's origins and evolution. As we delve deeper into the implications of the James Webb Space Telescope's discoveries, it becomes increasingly evident that the landscape of modern astrophysics is undergoing a profound transformation. The telescope, which was launched to peer deeper into space than its predecessors, such as the Hubble Space Telescope, has provided insights into regions of the cosmos that were once unreachable. The remarkable identification of 6 massive galaxies dating back to the early epochs of the universe raises crucial questions about the very nature of cosmic evolution. These galaxies are not only large, but also contain more stars than our Milky Way, even though they formed only a few hundred million years after the Big Bang. This challenges established ideas about the gradual nature of galaxy formation and calls for a reassessment of how we understand the early universe. The discovery of such massive, luminous galaxies at such an early stage in cosmic history suggests that galaxies might have formed much more rapidly and on a much larger scale than previously thought. Traditionally, the process of galaxy formation has been understood as a slow and steady progression, with galaxies taking billions of years to evolve from smaller, less organized structures into the large, complex systems we observe today. This slow progression was believed to be a result of the conditions in the early universe, extremely high temperatures and densities, which meant that the formation of solid structures was a gradual process. However, the new findings from the JWST indicate that some galaxies may have formed far earlier and more fully than our models would suggest, which could lead to a fundamental rethinking of the forces that govern cosmic evolution. In addition to challenging current models of galaxy formation, these discoveries also raise significant questions about the underlying processes that drive star formation. The newfound galaxies appear to be actively creating stars at a much higher rate than our own Milky Way, which forms stars intermittently. The high luminosity of these distant galaxies suggests that they may have been much more efficient in their star-forming activities, possibly due to conditions in the early universe that were more conducive to rapid stellar birth. This new insight into star formation may open up a wide range of avenues for further research, as scientists seek to understand the factors that influence star creation in the early universe. Moreover, the discovery of these massive galaxies pushes the boundaries of what we thought was possible in terms of cosmic structure. The prevailing model of galaxy formation, based on the Big Bang Theory, assumes that galaxies began to take shape much later in the universe's timeline. According to this model, galaxies were expected to form from smaller clumps of gas and dust over time, with complex structures emerging much later. The discovery of large galaxies from such an early point in cosmic history is a direct contradiction to this narrative, suggesting that our understanding of how galaxies form may be far more complex than previously assumed. This situation forces scientists to confront some uncomfortable truths about the limitations of current cosmological theories. It also presents an opportunity for scientific progress, as new discoveries often lead to the revision of old paradigms. The scientific community must now grapple with the possibility that the universe may be older than previously thought, or that the mechanisms behind galaxy formation were far more rapid and efficient than current models account for. As researchers continue to study these newfound galaxies, they will need to consider alternative models of cosmic evolution that can better explain these observations. In the larger context of scientific inquiry, this discovery underscores the importance of challenging established theories and remaining open to new ideas. The process of scientific discovery is not linear and is often marked by periods of uncertainty and revision. The history of science is replete with examples of well-established theories being overturned by new evidence. The discovery of these massive galaxies is a reminder that our understanding of the universe is always in flux, and that the most exciting advancements in science often come from questioning what we think we know. As technology continues to advance, and new instruments like the James Webb Space Telescope push the boundaries of human knowledge, it is likely that many more surprises await us in the cosmos, each one offering a new piece to the puzzle of the universe's origin and evolution. In the coming years, scientists will undoubtedly revisit many of the foundational concepts of cosmology. Whether these massive galaxies are a result of errors in measurement or an indication of a deeper truth about the universe, one thing is certain. The discoveries of the James Webb Space Telescope will be a key driver in shaping the future of astrophysical research. The implications of these findings extend beyond the realm of astronomy and have the potential to reshape fundamental theories in physics, offering new insights into the early universe, the formation of galaxies, and the very nature of space-time itself. This ongoing quest to understand the universe will continue to challenge and inspire scientists for generations to come.